Hi everyone, my name is Shubham Singh and I'm a PhD candidate at UT Austin. And today I'll present my work on analytical second order partial derivatives of rigid body inverse dynamics. The main motivation of this work is to accelerate the use of optimization based control methods for motion planning in legged robots. Optimization algorithms like DDP are at the heart of many model based controllers. Partial derivatives of dynamics and cost are a necessary requirement and often the costliest step for optimization algorithms. Hence, through this work, we compute the derivatives of dynamics accurately and efficiently, thus making optimization more feasible for motion planning. Differential dynamic programming, or DDP, is a very good candidate method for optimization in legged robots. DDP exploits Bellman's principle to optimize a cost function backward in time and results in an optimal control law with a state feedback term. This control law has terms with the first and the second order partial derivatives of dynamics as shown in this equation here. Often to cut down the runtime, an approximate version of DDP called the iterative LQR method is used, in which the second order cost terms are approximated by ignoring the tensorial terms. These tensorial terms are expensive and the existing literature does not readily extend to the tensor case. The downside of ignoring these terms is that we lose the quadratic convergence of DDP, shown by the red curve, and instead we only have superlinear convergence, shown by blue. Some of the work done to compute the derivatives of rigid body dynamics is listed here. For the second order derivatives, two main pieces of work are by Lee and Nana. In the work by Lee, they use a chain rule approach for second order derivatives. Although this results in an analytical approach, it gets expensive for high N. In the work by Nana, they compute the second order directional derivatives of inverse dynamics by using reverse mode automatic differentiation. Although it's very accurate, this lacks the potential for parallelization in the backward pass of DDP. In this work, we extend our previous work on first order derivatives, and for the first time, we present the analytical recursive expressions for second order derivatives of inverse dynamics for models with multi-degree of freedom joints and floating base. At the end, we also provide an efficient algorithm benchmarked in the C++ library Pinocchio. We quickly review the rigid body dynamics here given by this equation. We get inverse dynamics if we compute the joint torque given acceleration, and we get forward dynamics if we compute acceleration given joint torque. We consider all possible joint models from a 1-DOF revolute to a 6-DOF free motion joint. For this work, we only consider open loop kinematic trees with fixed or floating base. For the analysis, we use Featherston's spatial vector algebra to represent force and motion on rigid bodies using 60 vectors. The theory also defines spatial cross product operators denoted by cross and cross star. Since second order derivatives of tensors, an extension of spatial vectors to matrices and tensorial SVA is needed. For this purpose, we first extend the representation of the spatial motion vector to that of a spatial motion matrix with dimension 6 by n. In this spatial matrix, each column is a conventional 60 spatial vector. The spatial cross product operators are also extended to operate on spatial matrices and are represented by a tilde over them. The action of a spatial matrix operator results in a 3D tensor where each page corresponds to a column of that matrix. These matrix operators help us to redefine the identities derived earlier for first order work. An example of this is given here. We first define an open loop kinematic tree as shown here with the increasing numbering scheme from root to leaves. We also define the notation j less than I if joint j is in between root and the joint I. Now we define a kinematic quantity called the joint motion subspace matrix represented by this quantity S. S represents the spatial twist for all degrees of freedom of a joint. For a revolute joint, this simply is a column vector. Now the partial derivative of S for a joint I with respect to the configuration of previous joint J is shown. In terms of spatial vectors, this can only be done for 1-DOF of joint J at a time. But with the help of new spatial matrices and associate operator, the expression can be collectively written for all degrees of freedom of joint J at once, resulting in a 3D tensor. To get the second order derivatives of inverse dynamics, we first consider three cases by switching the indices I, J, and K. Then we take the derivative of the first order expression with respect to joint K. A second order derivative is defined by a 3D tensor and the order of the indices matter. In our case, we assume index 1 along the y direction, index 2 along the x direction, and index 3 along the pages of the tensor. We also know that since for a multi-DOF joint, these are Lie derivatives, this tensor block by itself is not symmetrical along the 2-3 direction. The resulting algorithm consists of two passes. Here, the first one is a forward pass and is similar to that in RNA. The second or the backward pass is a triple loop pass. In this, we loop over the indices I, j, and k from leaves to root as seen in the animation. The algorithm has a complexity of O and D square. Conceptually, this is similar to how the mass matrix algorithm has a complexity of O and D due to branch-induced sparsity. For accuracy and runtime check, we implement the algorithm in C++ library Pinocchio and in Featherstone's Spatial V2. Here we provide some runtime values in microseconds. We use two compilers, GCC and Clang, denoted by dark and light colors. Green bars represent the runtime for RNA. Red bars represent the inverse dynamics first order algorithm, while the blue bar represents the new second order algorithm developed in this work. For an 18-DOF HYQ, these numbers for first order and second order are 6 and 51 microseconds respectively. We also provide a runtime comparison using the automatic differentiation approach and a complex step approach in MATLAB. Compared to the complex step approach, we get speedups up to 100x, and compared to the auto diff approach, we get speedups between 1.5 to 3x by using the analytical algorithm. In conclusion, we presented for the first time the analytical second order derivatives of inverse dynamics for models with multi-DOF joints and floating base. Currently, we are working on comparing the runtime performance with finite difference, chain rule, auto diff approach in C++, and code generation techniques. For future work, we want to implement and try these fast and accurate analytical derivatives in a multi-shooting DDP algorithm for motion planning and robots. Thank you for listening.